thickness change in our sea ice, which is also very difficult.
So I've seen all these images of how sea ice is getting smaller every year, but are you guys able to tell if it's actually getting thinner?
That is exactly what we'll be really using ICESat to determine. You're right. Over the past few decades, we know that the spatial extent of our sea ice is getting smaller and smaller. What's also happening is it's getting thinner, and it's really hard to make thick ice. Thickness is kind of a proxy for the age of the ice. You can't make 8-year-old sea ice in 1 year. So we're getting thinner and thinner pack in the Arctic especially. What ICESat-2 will do is we'll measure the surface of the sea ice, and we'll measure the water next to it, either in the open ocean or in leads within the sea ice, where the sea ice is cracked and the ocean is exposed. We'll be able to use those two measurements, again with a lot of science that's very difficult, to get overall sea ice thickness and then ultimately sea ice thickness change.
So by comparing the actual measurement of how tall the ice is to these little cracks in the ice where you can see the ocean, that'll help you figure out how thick it is.
Exactly.
So that sounds complicated.
It is complicated. It's all right, we're NASA.
So you've talked a lot about how it's measuring sea ice, but it's also measuring ice over land. So what ice over land are we interested in?
We're specifically interested mostly in the Greenland and the Antarctic ice sheets, basically looking at how those ice sheets are directly contributing to sea level rise. The bulk of our fresh water around the globe is locked up in those two sources, and we really want to know what they're contributing to with respect to mean sea level.
Okay, so we're hoping to figure out how much they're contributing to sea level rise, because the melting ice, of course.
Exactly.
Okay. So how were those ice sheets formed? Like, where did they come from?
So ice sheets in our polar regions formed over millennia, and basically snow drops from the air. That's a very important distinction between land ice and sea ice. Our ice sheets are formed from water that started in the atmosphere. And over time, as you go through different seasons, this has stayed in place and hasn't melted through the summer seasons. We're getting to a point where we're starting to melt, especially around the edges, a little bit more in the summertime than before. So that's how our ice sheets are shrinking. The area of melt is outpacing the area where you're accumulating.
Okay. So we've talked about ICESat and ICESat-2.
Yeah.
And we know ICESat-2 is going to get us much better measurements with more dense measurements both along the track and across the track. But so ICESat stopped in 2009. What have you guys been doing since then?
So NASA also runs a major mission called IceBridge. IceBridge has been operational since 2009, and it will continue to just after the launch of ICESat-2. So probably about a year or so after launch. IceBridge has been using airplanes, lots of different airplanes, lots of different instruments to look at, especially what we know are the most rapidly changing parts of our ice sheets and the most interesting areas of sea ice. You can't do everything that you can do with a satellite, with an aircraft. We're targeting the fast-changing regions. IceBridge is wicked cool because it's the largest NASA airborne mission ever with respect to aircraft miles, number of aircraft, number of scientists involved, number of instruments on board. It's really cool and exciting. And it's even cooler than that, to be on these aircraft when they're actually surveying over the ice sheets is phenomenal. They fly at about 1,500 meters or 5,000 feet above the ice sheets or above the sea ice, and it's just unbelievable to be able to see this. It's got a stark beauty that some people appreciate, we certainly all do. It's just fantastic and exciting to be a part of.
So basically, since 2009, scientists have been going up in planes and filling in these satellite measurements by hand between the two missions.
That's exactly right. They do these in about 2 to 3 campaigns per year.
Wow. Well, in case you're just joining us, we are live from NASA's Goddard Space Flight Center near Washington, D.C. This is our satellite integration and testing facility. So if you step out here a little bit, you can see behind me all this equipment that we use to test satellites before they go into space. And we'll talk about that a little bit more in detail in just a moment. Right now we have some questions from the audience. So we have one question from Facebook. Kelly, will ICESat-2 actually measure through the ice?
So ICESat is a laser altimeter, so it's just measuring the surface. Our goal is to just look at the surface and then the surface change, and to calculate something about thickness or change in thickness through science and derived calculations after that. So no, just the surface.
But we can learn a lot from that.
Oh yeah, a ton.
So another question we have is, can this be used in any way to map forests?
So that's a really exciting thing about ICESat-2. The mission goal was associated with the polar regions, but the instrument itself is on as it goes around the Earth. So we're capturing all that data, and we've now developed a science team, or science definition team, that represents a lot of the different types of landforms, and science communities might be interested in that data. That includes atmospheric science, oceanographic science, vegetation, and inland water like lakes and rivers. So we do have what I would consider a global suite of data products addressing most of our landforms on Earth. So that's actually pretty exciting.
That's so cool. I didn't know that actually. So then, next question we have: is there any overlap between the plane missions we just talked about, IceBridge, and then the satellite ICESat-2?
Currently, we're planning on about 1 year of overlap. We will use the aircraft data to help us actually assess exactly how ICESat-2 is doing in the campaign. In other words, for data validation. So there should be 1 year of overlap between the aircraft and the satellite missions.
Okay, so you guys have gotten so good at these plane missions that you're going to be able to compare the data between the two to make sure the satellite's reading everything right.
Absolutely. We'll have a pretty all-encompassing approach. We'll have people on the ground, people in the air, and then, of course, the satellite above, what we call a nested validation approach for looking at these data products.
Great. So this right here is Phil Luris. He is the Deputy Instrument Systems Engineer. You guys were just with him in the clean room, although I don't know if you recognize him without the bunny suit on. But Phil, can you tell us a little bit more about what's next for ICESat-2? And that's the instrument you guys just saw in the clean room there.
So as soon as we're done aligning our lasers and making sure that they're aligned to the telescope so that we can get the signal back into the telescope and measure the ice accurately, we'll move into a simulation of the launch campaign. So the launch it's on a Delta II rocket. It shakes at about 12 Gs in all directions. And what we have to do is make sure that now that we put our lasers on, they're tightly aligned, they're very carefully aligned. Then we shake it at 12 Gs, really try to put some stresses in it. Then we see if they're still aligned. So that's a simulation of the launch cycle. Then the next thing that we will do is a simulation of on orbit. So in space, as everybody knows, there's no air. And it's kind of a cheat to use air, and air is kind of a cheat when it cools and heats things, airflow and fans and things like that. So what we do is we put our instrument in one of these thermal vacuum chambers behind me. We put our instrument in, we pull out all of the air. We pull it down to 0.0000 many O's 1 psi. There's almost no air left. And then the chamber itself has a cold shroud. It's liquid nitrogen flowing through a shroud, making that shroud go to -200°C. And so that's the simulation of the cold blackest space. Then we have heater panels that simulate the sun and also the Earth's surface. And we run a test that takes maybe 3-4 weeks to run a hot and a cold and a hot and a cold, and make sure that all of the designs that the thermal engineers have done will keep everything from overheating and also from freezing.
So how hot does that get?
The electronics boxes, I think we keep them at about 50 C, which is about 100 Fahrenheit. And then they've added radiators so that they never go above 50 C, so they don't cook. But once you put a radiator on something, then you have a chance for it to freeze. So we put heaters on things. And so it's a very tight balance of trying to keep something from overheating and also keep it from freezing. So they have a real big challenge on this one. Then the next thing that we do, we ship to Gilbert, Arizona, where we made up with the spacecraft, the ICESat-2 spacecraft. Orbital ATK is built at in Gilbert, Arizona. We'll made up to that, and we'll run one last vibration test, and then we go to the launch site. The launch site is Vandenberg, California. It's between Los Angeles and San Francisco. We'll launch out of there sometime next year. It'll launch south and go around in an orbit. That orbit is about 13 times a day, so it's about 91 minutes to go around the Earth. It's about 17,000 miles an hour, if you believe it. And it's a 91-minute orbit, so 13 times a day we'll see ground passes, we'll see communications at ground sites in Alaska, at Svalbard, Sweden, a few other places. And after 91 days of going around and around in this polar orbit style, we'll go over the same exact track. So every 91 days, the orbit will take you right over the same track, and you'll get that measurement that Kelly was talking about, the spring, summer, winter, fall of the same spot. So every 91 days, ISAT will continue to take these measurements.
That's great. So basically the spacecraft has to survive a really, really hard shake on this table.
Yeah.
And then temperatures down to minus 200 degrees Celsius and up to 50 degrees Celsius.
Right.
And we can test all of that right here in this room.
Yes.
Wow. All right. Well, I can't wait to see that. So we have a few more questions from Facebook. Just a reminder, we're live from NASA's Goddard Space Flight Center at the Satellite Integration and Testing Facility. And we just heard about all of the tests that ISAT-2 is going to have to go through before it goes into space. And they're going to happen right behind us over here. So we'll be answering questions in the Facebook comments after this broadcast ends, so keep putting them down there. We'll just answer a few more now, and so let's get started with our first one. Someone wants to know, are there opportunities for young adults to participate in this mission, things like this?
Yeah, NASA, the ISAT-2 project and NASA have been working with another NASA project called GLOBE, where students can, with their school systems, contribute to validation projects for our data products. That's hard to say. Anyway, schools can get together and go out and make measurements that we need to give us a global validation to tell us that we're doing a good job of getting that centimeter level accuracy and centimeter level precision all around the globe. So I encourage you to look online for GLOBE, and within that I encourage you to look for the ISAT-2 project associated with that.
Cool, so people can actually help us improve our science.
Yes.
That's awesome.
Great.
And then is there anything that you're particularly looking forward to seeing in the data?
I like to look at ice shelves, which are on the edge of Antarctica. They're the floating sections of the ice sheet. I'm excited to use ISAT-2 data to further examine ice shelves.
Cool. So I think we have one more question for Phil, and then we're going to sign off. Just a reminder, you can learn all about ISAT-2 and keep up to date with the latest on the mission here on this Facebook page or with NASA accounts across social media. So Phil, one more question for you. So we just saw the satellite in the clean room. How do you keep it clean when it comes out of there and goes into the rocket?
The contamination engineers do a bang-up job of covering it every time that we move it anywhere, every time that we use any piece of a crane operation or anything that might put a particulate on it. They make a gigantic gift bag. It's roughly 10 feet across, 10 feet down, and they tape it down around all the edges. They tape all the openings and basically put a bag around it. In addition, the really sensitive optics in the transmit path where the laser's hitting it, we purge those with nitrogen all day long and all night long. It's gaseous nitrogen, really low flow rate, but always blowing nitrogen into there. That way the dirt can't move upstream and get on the optics, because there's always a flow of nitrogen coming away from the optics. So every time that we move it out of there, it's in a bag. We move the purge along with it. A gaseous nitrogen tube is hanging out of the thing. When we're in the vibe cell, when we're preparing for that vibration test, there's a bag around it. We pull that bag away, and it's always purged. Same with our transport. So we have to get into a big transport container. It's a wide load on the back of a truck. Big wide load with air conditioners that keep the humidity down and the temperatures clean and are stable. And then it also has a filtering system. And again, the purge is running all the way across America and all the way to the launch site. The purge is running until launch day, until launch.
All right. Well, thank you all so much for joining us. This has been live from NASA's Goddard Space Flight Center just outside Washington, D.C. So this is our satellite integration and testing facility. And I hope you guys enjoyed hearing about ISAT-2, seeing it in the clean room. And remember, you can keep up to date with everything that's happening with the mission and its launch next year on NASA accounts across social media. So thank you so much for tuning in.
Thanks for tuning in.